Write each of the following complex numbers in the form a plus bi, where I squared is minus 1. Well, this is straightforward. We multiply the 3 into 2 minus 5i to get 6 minus 15i. Then we multiply minus 2i into 2 minus 5i to get plus 4i minus 10i squared. I squared is minus 1, so we minus 10 by minus 1 is plus 10. Plus 10 plus 6 is plus 16. Minus 15i plus 4i is minus 11i. Next we want to multiply this thing here out. 5 multiplied by 17 is 85. 5 multiplied by minus 13i is minus 65i. 4i times 17 is 68i. Plus 4i by minus 13i is minus 52i squared. Next we have a minus 1 into this product here. 5 times 17 is 85. 5 times 13i is minus 65i. 3i by 17 is 51i. Plus 3i by minus 13i is minus 39i squared. Now notice if we take the minus sign in here, these 85's actually cancel out to give 0. We have minus 65i plus 65i, that gives 0 also. Plus 68 minus 51 is plus 17i. And then we have minus 52i squared. Well, that's just plus 52, because I squared is minus 1. Okay, minus 52 by minus 1 is plus 52. We've got rid of these. Now we have minus 39i squared. That's plus 39i squared. Plus 39 by minus 1 is minus 39. 52 minus 39 is 13. So I'll write the real part of this complex number first and the imaginary part second. So we get 13 plus 17i. Now you might notice here that 17 minus 3i appears twice. So that means we can gather what's in front of 17 minus 3i together. We can put 5 plus 4i minus bracket 5 plus 3i together. So here's the 5 plus 4i, and if I take the minus sign in here, we get minus 5 minus 3i. We can put what I've circled together and multiply it by 17 minus 13i. This is just a distributive law for multiplication. So if you see a common factor in two expressions, you can take it out and just group whatever's in front. So I've grouped the 5 plus 4i with the minus 5 plus 3i. This makes life a bit easier actually. We get 4i minus 3i is 1i, so we have 1i times 17 minus 13i. Actually it makes this problem a lot easier. When I multiply I by 17 I get 17i. I times minus 13i is minus 13i squared. Now the minus 13i squared gives the real part. That's minus 13 by minus 1 is plus 13. And if I write down the imaginary part second, we get the same as before, but this is much quicker of course. So I suppose the moral of this example is that we should look out for a common factor if we have a number of expressions together. Now we've got what looks like a fairly tedious problem involving fractions here, but we can actually factorize a half out of each of these complex numbers. So we can write this complex number as 5 plus 7i divided by 2 squared. Might make it a bit easier. Just get a common denominator of 2. And there's also a common denominator of 2 in this second complex number, 5 plus I over 2 squared. So this is just 5 plus 1i over the common denominator of 2. Now we have to square above and below. Squaring the top part, square the first term, gives 25. Multiply first by second and double, as 35i times 2, 70i. And square the second term, 7i times 7i is 49i squared. And this is divided by 4, 2 squared in the denominator. 5 squared is 25, 5 times I is 5i times 2 is 10i. I times I is I squared, and we divide this by 2 squared, which is 4. Now we put these two fractions together, we have a common denominator of 4. So we have 25 plus 70i plus 49i squared. If I take the minus sign in here, we get minus 25 minus 10i minus 1i squared. So these 25's cancel out. Let's look at the real part. The real part comes from the I squared terms. Plus 49i squared is minus 49. Minus I squared is minus 1, which is plus 1. So we have plus 49 plus 1, that's plus 50. And we have 70 minus 10 is 60. This is divided by 4. So we have 50 over 4, which we can write as 25 over 2. And we have 60 over 4, which we can write as 15i. So just divide each of these terms by 4. So the real part is 25 over 2. We can also write this as 12.5. The imaginary part is 15. Sorry, I slipped up here. I forgot to check the answer. 49 by I squared is minus 49. So we have minus 49 plus 1 here, giving minus 48. So we get minus 48 divided by 4 is minus 12. So this is the correct answer. Just checked it. Which of Z1 and Z2 above is further from 0? Well, 0 here means the origin on an Argand diagram. So here is Z1 and here is Z2. So let's look at a rough plot of Z1. So the real part is plus 16, so we go plus 16 on the real axis and minus 11 on the imaginary axis. So Z1 is approximately here. Now, we want to see how far away it is from the origin. This distance is called the modulus of the complex number. We use Pythagoras' theorem essentially to get this distance. We imagine a right angle triangle. The two short sides are given by the real and imaginary part of the complex number. So this distance here is 16 and this distance here is 11. So the modulus of 16 minus 11i is the square root of 16 squared plus 11 squared. That's just Pythagoras' theorem. You can just remember to square each of these. Square the real part, square the imaginary part. Doesn't matter about the minus sign. If we square a negative number, we get it's the same as squaring the positive number. This will always work out to be positive. So that's the distance of the complex number to the origin. So we have 16 squared plus 11 squared. And we want to get the square root of this number, put this to the power of 0.5. So we get 19.4 for the distance of 16 minus 11i to the origin. Now let's look at 13 plus 17i. So we go to plus 13 on the real axis and up 17 units. And so it's going to be somewhere up here. It's only a very rough sketch. And the distance of this number to the origin is the modulus of it. So we want the modulus of 13 plus 17i. So again, it's just like Pythagoras. This distance is 17, this distance is 13. So we have right angle triangle. So the modulus of 13 plus 17i is the square root of real part squared plus imaginary part squared. If we calculate this, we get 21.4. So even though I've this badly drawn, the distance of 13 plus 17i to the origin is actually greater than the distance of 16 minus 11i to the origin. It should actually look more like this. So to one decimal place, this distance is 21.4 units, whereas the distance of the other number to the origin is 19.4. So which one is further from the origin? Well, clearly it's Z2. Z2 is the answer. Something I forgot to do in the previous part was to calculate this number here, which is called Z4. Well, we know that I squared is minus 1, so how do we get I to the power of 3? Well, we've done this before. We can factorize I cubed as I squared times I. I squared is minus 1, so we have minus 1 times I, which is minus I. So we can write this as 1 plus I plus minus 1, well that's just minus 1, plus I cubed, which is plus minus I, well that's just minus I. And you can see what's happening here. 1 minus 1 is 0, plus I minus I is 0, the whole thing is 0. Z4 is 0.